Hello everyone, in the last class we had studied about the properties of the aquifer. In this class we will derive an expression or an equation for the groundwater flow. Okay, it is also called as Laplace equation. Okay, what we will do here is we will write a schematic diagram of an aquifer. Okay, let's take the thickness of the aquifer as T, okay, and let's take the dimensions of this aquifer as W. Okay, look here, this is an aquifer, the thickness is T and it is kept as unity. Okay, this is the thickness and the dimensions is W and W. Okay, look here, as you all know, the discharge through an aquifer is given by Q equals A into V equation. Okay, now look here, where this V indicates Darcy's velocity. Okay, as you all know, Darcy's velocity V is equal to minus K into dH by dl, right? Okay, now what is K here? It is nothing but coefficient of permeability. Now what is dH by dl? dH by dl is nothing but hydraulic gradient. Now what is A here? It is nothing but area of the aquifer. How will you calculate the area of the aquifer? It is nothing but this W, okay, multiplied by the thickness, that is T. What will be getting? W into, let me write it as thickness. Right? Okay. Look here. If the water is entering the aquifer like this, if I want to calculate the area of flow, what I will be doing? I will be taking this W multiplied by this thickness. That's what I have written here. Okay. Let's substitute here. Let's substitute for Q here. Q equals what? W into thickness, okay, multiplied by minus K into dH by d. Yes, I hope you have understood the this equation, how this equation came. Okay, look here, now this thickness is taken as what? Unity. Then what? Let's take it as small t here, because we will be using capital T for transmissibility, okay, or transmissivity. Now what I will be doing here is W multiplied by 1 minus K into dH by D. Yeah. Okay, am I clear up to this? Now what I will be doing here is I will take up the transmissivity equation, that is T equals to what? Thickness of the aquifer multiplied by K. Okay. Now this equation of Q becomes what? Q equals W will remain as it is. For K multiplied by unit thickness, you are going to take it as what? Capital T. Okay. I will be telling once again, just look at this equation. What I will be doing, I will take the product of the coefficient of permeability K and the thickness, that is unity, and I will put it as what? T. Okay. So this equation will be what? Minus T multiplied by dH by D. Yeah. Okay. I hope you have understood up to this equation. If you have understood up to this equation, further we can derive the equation easily. Okay. First what we did, we took up the schematic representation of the aquifer, we wrote the dimensions, and we took up what? The discharge equation for the aquifer, and we took the equation of Darcy's velocity and we substituted here. Next what we did, we took the equation of transmissivity and we calculated the area of flow, and by getting to know about the area of flow and about the transmissivity, we substituted to get the equation for Q. Okay. Let us write this equation as 1. I hope you have understood up to this. Clear? Now, now look here, I will write a diagram once again. Okay. Look here, this is discharge equation. What I will be doing here is, I will write the discharge equation in the horizontal direction, that's why I will write it as Qx comma I. Okay. This Qx comma I indicates the quantity of the water which gets into the aquifer in which direction? X direction. Okay. And I will write Qx comma O. This represents quantity of the water which gets out of the aquifer in the x direction or in the horizontal direction. Look here, I am going to write it as Q y comma I. Similarly, I am going to write Q y comma O. What does this represent? The quantity of water getting into this aquifer in the y direction and quantity of the water which gets out of the aquifer in the y direction. Okay, look here. Now what I am going to do is, I am going to write this equation that is applicable in the x direction. Okay, look here, Q x comma I equals W into minus Px into dH by, look here carefully, I am going to write it as x here, okay, and I am going to write it as x comma I. Okay. Look carefully, I have written dx instead of dl because here it is travelling in the x direction and it is covering the distance of x. Okay. Am I clear about this? Now the same equation is applied for the quantity of the water going out of the aquifer in the x direction. Okay. This will be what? W into minus d y into dh by dx x comma. Okay. Similarly, what I am going to write? I am going to write it for y direction also. Am I clear up to this? Now what I am going to do is, I am going to calculate the volume of water retained in the aquifer. So what I am going to do here, I am going to calculate the volume of the water which is retained in the aquifer. Okay. For that, what I am going to do, I am going to take the difference of quantity of water which gets in and quantity of the water which gets out. Right. Okay. Look here. Right, what we did, we calculated volume of water retained in the aquifer with this equation. Okay. Next, as you all know, the storativity or storage coefficient is given by what? Quantity, or you can just write volume of groundwater which gets out of an aquifer per unit surface area per unit drop of the head. Okay, you can just refer the definition and the diagram of the storativity, where we have written it as volume of the water which gets out of an aquifer or which gets into the aquifer per unit surface area of the aquifer and per unit drop down of the head. Right. Okay. And that is why I have written it as dH by dt. Clear? Okay. Now look here, I need the value of the volume of the groundwater, that is why I took this equation of storativity. Okay. You can see this is LHS and this is RHS. LHS is what? Volume of the water retained in the aquifer, and RHS is this equation. For the LHS, I need to get an equation, that is why I have took the storativity equation, where I will get the value of volume of groundwater. Clear? Now look here. So volume of groundwater water equals storativity multiplied by surface area, let me write it as SA, and multiplied by what? dH by d, right? Now, how will you calculate the surface area? This is what? The schematic diagram of the aquifer. This is W and this is W. If I need the surface area, what I will be doing? W square it will be. So, this will be what? Storativity multiplied by W square multiplied by dH by d, right? Okay. So, this gives me what? The RHS portion of this equation. Volume of the water retained in the aquifer is given by the equation ST multiplied by W square into dH by dt. Now, what I am going to do is, I am going to substitute the equations for dxi, dxo, sorry qxi, qxo, qyi and qyo from this equations. Okay, look here. For qxi, this will be what? W into minus dx into dH by dx okay, and this will be what? I substituted for qxi minus qxo from these two equations. Now I am going to substitute for qyi and qyo from these two equations. Look here. So this will be plus okay. If you look at these equations, what is common here? You have W square here and you can see what is common here in this equation. You have W as common, okay. And what I will be doing is, I will be taking out the W as common and you will be having what? Minus dx into dH by dx I have taken W as common from this entire equation, this W, and in this W square, one W gets cancelled, okay. I am going to write the further equations here. So what will remain? Look here, this W and this is in this W square, one W gets cancelled. What I will be doing is I will bring this W to the denominator of this. Look here, I will going to write and this is equal to what? ST multiplied by W multiplied by dH by D, right? Okay. Now look here. In this I have taken out one W and I have just cancelled this W and have written the remaining equation, right? Okay. I will bring this W to this denominator. This is LHS and this is RHS. I am going to bring this W to the denominator of this equation, and let me say here, if the value of this W is too small, this difference of head can be expressed in terms of second degree differential equation. Okay, I am going to write it that directly. Look here. And one more thing, here the Tx and Ty represents what? Transmissivity, and if you remember the equation for transmissivity, it is T equals what? Q divided by dH by dL, right? Okay. This is rate of flow per unit drop of hydraulic gradient. Okay, and we will assume that transmissivity is same in all the directions. Okay, so with that, this T will be same for all this equation, and you can just write it as what? Bring this T to this denominator, this will be what? D square H divided by dx square plus d square H divided by dy square equals storativity St divided by transmissivity into dH by dt. Okay, this is two-dimensional groundwater flow equation for the unsteady flow. Okay, why I am saying unsteady flow? Because for the steady flow, this dH by dt will be equal to 0. Okay, I will write here. Okay, this is two-dimensional equation. I am going to write the three-dimensional equation here. D square H divided by dx square plus d square H divided by dy square plus d square H divided by dz square equals St divided by T multiplied by dH by d, and this is for unsteady flow. For the steady flow, what will happen? dH by dt will be equal to 0, and this can be represented. This is the three-dimensional equation for the groundwater flow, and if this dH by dt is equal to 0, that is for the steady flow, then this equation will be equated to 0, and we can express in this form, and this equation is called as Laplace equation, or you can just say a general groundwater equation.